Okay, so today's lesson is limits from tables. Before we go on, I just want to draw your attention to going back to the worksheet from yesterday. I have added in the answer key off to the side. A couple quick notes about 5F and 6C that I've added in there. Also looking at K and L for this question 10. And those are kind of the big ones. And just watching this language in like 19 and 20 again, and in K and L, and being able to really interpret those. So if you have any questions about that, please let me know. Post in our little peer support place over here. I don't see any questions thus far, so I'm assuming that you are good to go. But we'll dive right into our lesson. It shouldn't be too long today. I'm going to pause while I do some calculations as we go, just to save you some time of like watching me write. So all of a sudden numbers will appear. Feel free to pause the video to jot them down or to do the calculations on your own. So we're looking at some functions now and looking at limits from tables. So whereas when we have a graph, it's very visual. Using tables to interpret limits, it also becomes very apparent if you choose the right data points to analyze, but it's really important that you're choosing those right data points. So we're going to work with this first function here. So f of x is equal to x squared minus x minus 6 over x minus 3. So your inclination might be to simplify this and say, okay, well, that's the same as f of x equals x plus 2 if there's a non-permissible value at x minus 3. Okay, so you can simplify it to work with it in this form, or you can work with it in its entirety, whichever way you want, as long as you have that non-permissible value stated as well. Okay, so if we're looking at the first question, now something I haven't done up to this point, and I'll do it in this first example, maybe I'll zoom in a little bit here, is looking at example 1. If we're asking for the limit as x approaches 0, and instead of writing f of x, you can also write the function in its entirety. So you could write x squared minus x minus 6 over x minus 3. That is totally fine. That's an entirely acceptable notation. For efficiency's sake, I'm going to stick with using that f of x term, knowing that I'm referring to this question or this equation for the questions that I'm doing immediately under it. So how do I use a table to do this? Well, that's an excellent question, and it's all about choosing values. The first thing I'm going to do is make a table of values, and I'm just doing it horizontally for some consistency's sake, but you can always do it vertically. Just make sure you're paying attention to where your independent variable is listed and your dependent or your output. So if I'm looking at 0, I can actually calculate the value at 0, but as we know, it's not necessarily the value at 0 that matters, but rather approaching it. So for the sake of it, I'm just also going to calculate for 0 because it is not a non-permissible value, so I know it's defined. Okay, and I'm going to choose some numbers that are approaching the 0 from the left and from the right. So again, I put it in the middle so that I have space to approach it, in this case, from the negative side and the positive side. So I can choose, like, I want to choose some numbers that are pretty close to 0. So like negative 0.999 and negative 0.99 and negative 0.9. You're like, okay, Miss Conrad, well, why did you choose that? Why didn't you go with like -3, -2, -1? I don't want to do that because those are too far away, and that's not really going to give me the best picture of what's happening right as we're approaching 0. For the same reason, I'm not going to go like -0.3, -0.2, -0.1. That's much closer to 0, but I want to get, oh, so maybe I should be doing this instead. as I'm looking at these numbers, being like, maybe that doesn't make sense. If I do negative 0.1, negative 0.01, negative 0.001, okay, that's getting close. That looks much better. That's getting closer and closer to that 0 value, getting smaller and smaller and smaller, approaching 0. So again, we don't want these because although it's better, it's not the best option. Okay, from the other end, I might start at 0.0001 because I can get even closer, or I can just kind of go with symmetry and go 0.001, 0.01, and 0.1. And 3 is going to give me a decent picture. So from here, I'm going to plug these values in and I'm going to calculate my output. So if I go in here, I get 1.9, 1.99, 1.999, 2, and then 2.001, 2.01, and 2.1. So as I approach 0 from the right side, and look in terms of looking at my y values, I'm getting closer and closer to 2. As I approach from the left with my x values, my y values again are approaching 2. Therefore, I can say that my limit as x approaches 0 for this function is going to be 2. Great. But what if I ask a different limit? What if I ask the limit as x approaches 3 for the same function, x squared minus x minus 6 over x minus 3. And as I'm looking at this, I'm like, I don't love this non-permissible value notation. My non-permissible value is at x equals 3. Okay, so again, I'm going to need a table of values and I'm going to need to choose some numbers. Now in this case, if I'm looking at 3, I know that it's a non-permissible value, so it's going to be undefined. Okay, but again, I can choose some numbers that are approaching 3. So again, we want to close that gap as much as we possibly can. So starting farther out, we might start at like 2.9 and go, okay, well, 2.99. 2.999, getting infinitely closer to 3 if we continued in that pattern. And again, 3.001, 3.01, 3.1. And that should give us a good picture. So when we go ahead and do this, we see, okay, well, this is 4.9, 4.99, 4.999. Okay, well, that's great. What about over here? We've got 5.001, 5.01, and 5.1. So again, on the right-hand side, we're moving away from 5, slowly growing away. On the left-hand side, we're slowly getting less than 5. But as we approach, if we look at it as if we're coming in towards 3, both are approaching 5. So I would say that the limit of this equation is 5. Even though it's undefined at 3, we can still have that limit. So seeing that same piece. So it's really all about choosing your values as to what gives you the best picture. And in terms of estimating, gives you your best estimation. So we can do the same with our next function. So if we take the limit as x approaches, say, positive 2 of f of x, and again, I'm just going to abbreviate filling this in, then I can use a table of values to help me out. So if I'm approaching 2, then I can choose maybe, and I might work with fractions this time in terms of how this looks. I could go with like 1/10, 1,000th, 1/10,000th. As I'm getting smaller, I can go with, oops, sorry, that's not accurate. So again, being really conscious, I want to get close to 2 without actually, and I was trying to think of answers that would change. So maybe going with 1.9, 1.99, 1.999, and 2.001, 2.01, 2.1. So you'll notice a pattern in terms of decimals as to what you're working with. From here, same idea happens. We're going to plug these values in, see what it spits out from the function, and we'll look at that. So again, once I use my calculator in this case to fill in these values, I'm able to see, okay, well, as we approach, we're getting towards 0.25 from both ends, and in actuality, my value at x equals 2 is 0.25. So I can say that that's the limit, 0.25. Okay, but if I ask for the limit as x approaches 0, we might find some more interesting things. So again, I've got my table of values. I can maybe plug in 0, but I know it's going to be undefined because that's one of my non-permissible values. So again, I'm approaching 0. Now I won't mess this one up because I already did it up there. So choosing something like negative 0.1, negative 0.01, negative 0.001, and then building 0.001, 0.01, and 0.1 as my values. So again, getting infinitely closer to 0 on both ends of things. So I'm going to punch these into my calculator and see what I get. Okay, so once I fill in these values, I use my calculator to help me out, plug these x values into my denominator and square them before calculating it, and I notice that they're getting bigger and bigger, and if I went to even smaller numbers, they would continue to do so, like smaller numbers being closer to 0. So in this case, my limit is actually approaching positive infinity, and I can say with certain that it's positive infinity because it's positive 1 million on both sides. If one side had been going to positive 1 million, but the other had gone to negative and gone into the negatives further, then my limit would not exist. But because they're both getting bigger and bigger and bigger and positive, I'm able to say it's approaching infinity. So that's kind of what we're looking at here. So it's crucial that we're choosing those good values. As you saw, it's very easy to choose some bad values and kind of get distracted as to what our values are and what would be helpful, but choosing those decimals that get closer and closer are your best bet to being successful. So there's a link in our schedule, and you can head there to access Khan Academy. There's a little kind of quiz. I think it's like 4 questions just to practice this whole principle of using tables to estimate limits. This isn't a huge part of the course, but it is a valuable little tidbit just because we can numerically see exactly where the limit is going to be. So again, let me know if you have any questions, and tomorrow I'll post another video.